Hi everyone, welcome to the first part of lesson 4. This one's about predictions. Consider a theory. A theory in science is just an explanation of what people think is going on and how people think things work. We need to consider whether or not theories are true. This is the business of science, and if theories aren't true, we replace them with better explanations and so on. When we're trying to work out if a theory is true, we need to consider whether it's consistent with what we know already, whether it's consistent with theories that are well established already. But what I want to focus on in this lesson is the predictions derived from theories. Can we confirm them? Predictions come from theories in the sense that a theory is explaining how the world works. You should be able to extract fairly specific predictions from that theory. To test those predictions, you design an experiment and you test the hypotheses against the outcomes of the experiment. The experiment is designed to test the hypotheses, as we know. An experimental hypothesis is simply what we expect to happen if the theory is true. Straightforward so far. Let me use an example. Dr. Rebecca Pincus will talk about cognitive dissonance as part of her lectures later in the semester. Festinger and Carl Smith's idea that a person comes to believe in what they do to reduce internal conflict, to reduce this cognitive dissonance. Simple, ingenious study. The participant comes into the lab and is asked by the researcher to do what turns out to be an incredibly boring study. They're just turning the pegs, those square things, they're just turning them for however long. It's phenomenally boring. That's not the study though, that's just the setup for the study. The participant is then asked to explain to the next participant that the study was really fun, it was really interesting, it was very enjoyable. They're either paid nothing to do this, they're paid $1 to tell this lie. In fact, I think the control condition is they don't have to do it at all. Or they're paid $1 to tell what is essentially a lie. It was very enjoyable, I had a lot of fun. That's a lie. Or they're paid $20 to tell this lie. Now, if you're paid $20, and this was a 1959 study, to tell a lie, you know what? That's fair enough. That's good money to tell a lie. You know, there's no cognitive dissonance. $20 to tell someone that horrible thing was fun? Yeah, okay. There's no internal conflict then. Why are you lying to someone? Well, because it's $20. $1? It's not really enough somehow to tell someone that the study I just did, which was awful, was actually interesting. So there's cognitive dissonance. And so Festinger and Carl Smith hypothesized that the person resolves their cognitive dissonance, not enough money to lie, by convincing themselves that it was a fun study. And so this is how they derive their experimental hypotheses. Paid $20 to lie? Well, the hypothesis there is those people will report that the study was boring. But if someone's not paid enough to lie and goes ahead and tells that lie to someone else to reduce cognitive dissonance, the hypothesis there is that they'll actually think the study was enjoyable. They'll convince themselves of this case. They'll delude themselves. This is exactly what was found. This is the data from this old study. Those paid only $1 rated the tasks as more enjoyable. But if you think back to lesson 2, where they had a behavioural measure too, they were also more likely to say they'd participate in a similar experiment. They really had fooled themselves. It's fascinating, isn't it? But there's more on that in the social psychology lectures. I was just using it as an example. An experimental hypothesis is what we expect to happen if the theory is true. The problem with experimental hypotheses and just focusing on those predictions that we hope will happen, we think will happen, is we face a terrible cognitive bias, confirmation bias. This is where we seek out evidence that confirms our views, or we have evidence already, but we only interpret it in a manner, a biased manner, which confirms our beliefs. It's something you can imagine humans are vulnerable to every day. Let me give you a tip. You've become a bit of a superhero by this lesson. You know a lot more about logical fallacies, evidence, science, research design, and so on. Should you go to your communities, your relatives, your friends, and start arguments with them? Well, here's my tip. Before you start any kind of argument with someone, ask them this question. What evidence would convince you that you are wrong? If they just look at you like you're crazy, best not to have that argument, because that suggests that they have not even considered the possibility that they're wrong. How productive is your conversation going to be with someone for whom there is no chance they will ever consider that they're wrong? Ask them this question. Now, there are some people for whom what they believe can never be falsified, can never be questioned, because they've set themselves up in a bit of a bubble. The media never tells the truth. Someone in that position, you're never going to have a productive conversation with them, because nothing you say, it could ever be considered a fact then, confirmed. God put the fossils in the ground to mislead people. Okay, well, we can't disconfirm that. What a mischievous, awful, pathetic God that would be if that was the case. No order or reason in the world. Ouch, I'd hate to live in that universe. But if someone sets themselves up like that, they're basically saying, whatever you say, I'll have some kind of ridiculous conspiratorial answer for you. Or signed as a bribe by Big Pharma to fake results. In fact, where is that pile of money I got for lesson 1 about vitamins? It must be lying around here somewhere. Know when not to have a conversation. Know when a conversation is just not going to be productive. Someone like that, they're led by confirmation bias. A scientist, however, if you ask a scientist what evidence would convince you that you're wrong, they should be able to tell you, because not only will they have thought about this, but they would have designed experiments to falsify their views. $1 or $20 won't make a difference for the cognitive dissonance study. We will, evolution's easy, we'll find dinosaur bones in sediments above mammals, which would completely ruin everything. It's never happened, but it's very easy to falsify theories of evolution. Or about vaccination, death rates will be the same, sadly, in those people who are vaccinated and those who aren't. Well, that's not the case. But that would be the situation if someone was wrong about vaccines. Theories need to be falsifiable. And we need to find a way to get around confirmation bias. $1 or $20 won't make a difference. What is that an expression of? Well, this is what we call the hypothesis of no effect. The hypothesis of the theory is wrong, otherwise known as the null hypothesis. And I've got the little script there. It's a big H with a little O, null hypothesis, or HO as some people. It's not HO, it's a subscript of O. The null hypothesis. The null hypothesis is the hypothesis of no effect. Now, as scientists, we want to find things, we want to discover things, we want to show that our theories, predictions can be confirmed. So this null hypothesis of no effect, we're motivated to reject it. We want to reject it. But we need to keep it in mind, because not only does it play a role in the background, in the statistics, but it's part of the logic of setting up a design such that it rejects, disproves the null hypothesis. Consider the example I used in the very first workshop about McDonald's hamburgers. When you just see this claim, this so-called theory, McDonald's hamburgers are full of nasty preservatives and never mold or age as a result, and you rush out and you seek confirming evidence only, let's get one McDonald's burger only and stick it in the sun for 6 months. Oh my God, there's no mold. Yeah, because it's dried out and it's in the sun. We're very good at criticizing things, humans, though. And the thing about null hypotheses that we want to reject is that they help us. Even if we're struggling with the logic of our predictions or our claims, a null hypothesis can suddenly activate something in us and motivate us to understand what we're doing wrong. If we start from a different position, and this would be a way of expressing the null hypothesis of hamburgers, if you like, we're motivated then to attack that, and we will do something useful. McDonald's hamburgers are no different to any other hamburgers. Let's disprove that. What do we need to disprove that? Okay, we'll still grab a McDonald's burger and test and sit it there for 6 months. But you know what? We're motivated to show that it's different to other burgers. So, okay, we're going to have to do the same with an organic burger the same size, and lots of other conditions. We're this is kind of a commentary on science itself. Science, the mechanisms of science recognize human cognitive biases, like confirmation bias. So our systems have to be set up to allow us to get around them, so that research itself isn't hopelessly biased and we're just proving things and confirming things and never actually attacking things. So the null hypothesis of no effect is really, really useful. It plays a role in the mathematics, and that's coming up in a few lessons' time, but importantly, it gives us the logic to get around our biases. The other advantage of the null hypothesis is it's very precise numerically. This is why it plays a role in the maths. Mean 1, those paid $1, minus mean 2, those paid $20, equals 0, a very specific number. We can then apply our maths to see if we've got non-zero differences, unlikely to be due to chance. And again, linking it back to cognitive dissonance, those given $20 will say the task is just as enjoyable as those given $1, and that was rejected from the research. There is an alternative though, and it's called the alternative hypothesis. This, I guess, is the one we want to be true, and it's relatively unexciting compared to the logical wondrousness of the null hypothesis. It's just, okay, the null is the conditions are equal. The alternate would be the conditions are not equal. Okay, one's bigger than the other. For example, those given $20 will say the task is less enjoyable than those given $1, which turns out to be the finding. So that's the alternate hypothesis. H1, you'll see it. It's kind of less important right now. Nevertheless, what we're aiming to do in research with our null hypotheses is reject them. Because if we can reject the null hypothesis of no effect, something's happened. We have evidence of an effect. This is something really important to understand though. If we retain the null hypothesis, we fail to reject it, we don't have any evidence of anything. Retaining a null hypothesis is not the same as accepting the null hypothesis. I know you dig around enough textbooks, someone said somewhere, oh, we accept the null. The logic is all wrong, it's messed up. You shouldn't be accepting nulls, you're just retaining them. It's a weaker word. We're letting it hang around. We're not, okay, you're there standing in our house, but you haven't been invited to the party. You're not, okay, just hang around there. But we're not, let me explain it with a few examples. The justice system, for example, in Australia is set up to be combative. You've got the prosecution and defence. And long story short, someone who's accused of a crime, they are presumed innocent until proven guilty. And so the task of the court is to prove them guilty. That's all that the court is doing, trying to prove them guilty of the crime. When someone is not proven guilty of a crime, we let them free under the presumption of innocence. At no point did anyone in the courtroom try to prove someone innocent. So it would be a failure of logic, and you see this often when people are released because they've been found not guilty. They'll stand on the steps of the courthouse and say, I have been proven innocent. No one was trying to prove you innocent. In fact, if it was a criminal court, for example, there'd have to be quite a lot of evidence against you to actually get to trial in the first place. So if anything, maybe on the balance of probabilities you did something, But the fact of the matter is that the court tried to prove you guilty and failed, so we're letting you free. No one proved you innocent. Another way of explaining retaining the null hypothesis, just in terms of logic, absence of evidence is not evidence of absence. Okay? If you go to the picnic on Sunday and Sharon isn't there, you have evidence Sharon didn't come to the picnic. But if you don't go to the picnic on Sunday, well, you didn't see Sharon, but you have no evidence she wasn't there. Absence of evidence is different from evidence of absence. Okay, I'll try one more example, see if this works. You're in love with someone. You're dating someone. Do they love you? Well, maybe. Or maybe they haven't found someone better. Okay, this is kind of a cruel example, but I often see when I do this live, I see people in the audience, okay. And that's kind of what the null hypothesis is. It's a very cruel thing, but when we retain the null hypothesis, we're just kind of letting it hang around, You've got a partner, you've got a boyfriend, a girlfriend. Does that mean you're in love? It might just be that you haven't found anyone better. You just think, and that kind of seems shocking, but that's exactly how science works. The current understanding is not something that is worshipped or, oh yes, this is, quite the opposite, as I explained from the very first lesson. We attack the current understanding. We make our careers on trying to destroy the current understanding. So that would imply that the current understanding is something that we let it hang around. It's the best that we've got at any point in time. But if something better comes along, boom, we'll get rid of it. So failing to reject the null doesn't mean that we're accepting it. It just means we're letting it hang around. An important logical distinction. So the steps I've described then is we derive the hypotheses from theories. We design experiments to test those hypotheses, and you're all up to speed on your research design now, how we might design experiments. Ultimately, though, as part of those experiments, they need to attempt to disprove the null hypothesis of no effect. And if we can do that, then we have evidence that something has occurred. This is kind of where we're headed, because there's a few bits and pieces in the lesson so far that I'm yet to combine. Lesson 5 is when they all come together. We're looking at a treatment, for example. Those red dots are scores on the effectiveness of the treatment. Positive is good, so 2 people haven't gone that well, but a lot of them have gone quite well from the treatment. We're trying to work out whether it's effective or not. Our null hypothesis is the treatment is not effective. We're going to try and disprove that. Our research hypothesis, our experimental hypothesis is hopefully that the treatment will work. Okay, so that's null hypotheses and confirmation bias and experimental hypotheses, lesson 4A.